Assalamu alaikum. I am Wajid and my registration ID is 16T37. So in today's lecture I am going to discuss about the pole zero placement method for simple infinite impulse response filters. So in the last lecture we saw different techniques for the IIR filters. So in today's lecture I am going to discuss about the pole zero placement method for the simple IIR filters. So first of all, two things which we kept in mind. We first of all have to draw the circle. Here we have the poles. Here we have our pole value, and this is our also conjugate pole. So this is our Z is equal to E bar G of omega. So first of all, two things kept in mind. If we want to increase our magnitude, then we will place the pole. For example, our magnitude of our system is very much less, then we have to increase the magnitude of our system, then we will place the pole. And if we want to decrease the magnitude of our system, then we will place the zeros method, then we will place zero at that place. So the main benefit of this method is that this method deliver good performance when band pass and band stop filters have narrow bandwidth. So we use these filters for good band pass and band stop filters. So here we have four kinds of filters. First of all, we will looking toward the band pass filter, and then band stop filters. These are the second order filters, and then looking toward the first order low pass filter and first order high pass filter. So first of all, for second order band pass filter, we have been giving the specific band to operate our filters. Here the diagram of this pole zero will be as pole, this will be the pole and this will be the zero. The zero will be placed here and the pole will be placed in between these two values. This is first quadrant, fourth quadrant for our values in between positive and negative values. So these are the simple method. The things which we kept in mind is that we have to remember the formulas. The first of all formula for R is equal to radius. This is our basically radius. R is equal to, for finding this value, R is equal to 1 minus bandwidth for 3 dB filter divided by f of s. F of s is the sampling frequency. BW is equal to bandwidth and multiplied by pi. So then next thing which we will calculate is theta. Theta is equal to FO. What is FO? FO is the central frequency, narrow band central frequency, and then F of divided by F of S multiplied by 360. F of S is also the sampling frequency. And then next thing which we will find is K. This is our scaling factor which we have to find. And then at the last we will find the transfer function. What is transfer function? H of Z values we will find here the transfer function of our system. So let's I have the example of 8.17. I have been given that the sampling frequency is 8000 Hz and bandwidth is 200, and f0, which is the central frequency, I have been given is 1000 Hz. So what I have to find is transfer functions using the pole zero displacement method. So first of all, what will I do here is first of all calculate the value of R. By calculating the value of R, what I get here is 1 minus 200 divided by 8000 multiplied by pi. So after putting these values in calculator, I get my value 0.9215. So my R value should be in between 0.9215 or less than 1. In this value, this filter is considered to be very much greater for our performance or good. It considered to be good. So in the next step, what I will find is calculate the value of theta. What is theta? Theta is our angle along the pole line. So for calculating this value, f0 divided by f of s multiplied by 360. What is the centered frequency f0? This is the 1000 divided by f of s sampling frequency, which is 8000 multiplied by 360. When I evaluate this value, this gives me the 45 degree. So in the third step, what I will find is K. What is K? K is the unit gain. So I will put up the value in the formula as 1 minus R into 1 minus 2 into R cos of 2 theta. Theta here is 45 degree. 45 multiplied by 2 will become 90 degree plus R square divided by 2 sine of 45. So after calculating these values, I get here 0.0187. And the final and last step, what will I do here? I will put up the h of z. This is our transfer. This is my transfer function. what I do here, putting all the values of my function into the transfer function, and this gives me the value. I can here simplify my expression, but this is alright and okay. So in the next example, I am going to discuss about the second order band stop filter, which is also known as the notch filter. So in the last I discussed about the second order band pass filter, and in this I will discuss about the band stop filter. So here we also have to follow the 4 steps. First of all, I have to calculate the value of r. This is the same formula to calculate the value of r, and then theta, which is the angle made by the pole, and the next thing is k. Here the formula is changed with respect to the band pass filter. This is for band stop filter. And the next thing is h of z, which is our transfer function. For our transfer function, we find our different values. So I'll look at the example. We have been given that sampling frequency is 8,000. Sampling frequency is 8,000. Bandwidth given is 100 Hz, and f naught, which is our standard frequency, that is given 1500 Hz. So I have to calculate the transfer function using this is for band stop filter. I have to calculate the transfer function using the pole zero method. So again repeat the step. What will I do here? Calculate first of all the value of r. 1 minus BW divided by f of s. BW is bandwidth, which is given as 100, divided by f of s, which is my sampling frequency, which is 8,000 multiplied by pi. This gives me the 0.9607. This is the good value for our filters. So next thing which we calculate is theta. What is theta? Theta is the angle. So 1500 divided by 8,000 multiplied by 360, this will give me the 67.5 degree. And the next step is k. K is equal to unity gain 1 minus 2. Similarly, the value of 1 minus 2 or cos of theta plus r k divided by 2 minus 2 cos of theta. So by putting this value in my system, what I get here? I get here the value of k is equal to 0.9620. So in the last and final step, what I calculate here is 0.96. Putting all these values which I calculated, the value of r, theta and k, this values in the my transfer function, which is h of z. So this was our section of the second order band stop filter, which is commonly known as the notch filter. So in the third and last thing, the last one is the first order low pass filter design. So in first order low pass filter design, we have the two cases. First case is that when our cutoff frequency f of c is equal to f of s divided by 4. F of s is our sampling frequency divided by 4. And second case is when our cutoff frequency is greater than f of s divided by 4. So for our cutoff frequency less than f of s divided by 4, we have the three formulas here. This is our alpha. Alpha is nothing but the value where we place our pole. This is the value where we place our pole. So this will become 1 minus 2 multiplied by f of c divided by f of s cross pi. This also gives value should be 0.9 in between 0.9 to 1. And next thing is transfer function, which is h of z is equal to k into z plus 1 divided by z minus alpha. And the third one thing is k is equal to 1 minus alpha divided by 2. Similarly, the case is alpha is equal to 1 minus 2, 1 minus pi plus 2 f of c divided by f of s multiplied by pi. This value should be in between minus 1, or should be greater than minus 1 and less than or equal to minus 0.9. So similarly, we repeat the step here, second and third for our value. So this is our end of the video. So thanks for listening. As always, God bless you all. Thank you.